Okay, so the goal of today is to do some Bayesian calculations. We introduced the Bayesian paradigm, and so to give a quick recap of that, in the Bayesian setting, the key to encoding uncertainty is to use probability distributions, and so the two key distributions that the terminologies for them that we use a lot is the prior and posterior. Okay, and so the prior distribution is, so let's just do a quick recap. So the prior is what we know about the quantity before we see any data. So it encodes our prior beliefs, and then in the Bayesian paradigm, you combine that with our data, and so the data is usually expressed via a probability model and a likelihood function, and then together we get a posterior. And so the posterior is what we now believe about this unknown or uncertain quantity after we have seen the data. And so when we then take the results of our analysis, they're summarized in the posterior distribution, and from there we give estimates of unknown parameters or other quantities of interest based on our model. So today I want to go through a specific example, which is how to do this sort of calculation using the most commonly known, most famous distribution in statistics, namely the normal distribution. So just for the benefit of, so we're all on the same page, I want to first make sure we see the picture of the normal distribution. This is the very famous bell-shaped curve. Okay, so it's used to describe many things like height, IQ, measurement error. So that's a common one. And so when we introduced Bayesian statistics, I drew some pictures of probability distributions, and so in this sort of picture, so this is what the curve looks like, but to actually work with it mathematically, of course, we need to write down its functional form. Okay, so let's say, so we've been using the letter y for, so we can say this is, this x-axis here captures the values of the distribution, and then how high this curve is captures its probability density. Okay, so that's plotted on the y-axis here. So in particular, working with probability distributions where you see there's a high density, it just means like the values here are more likely. Okay, so how do we express the shape of this curve as a function? So let's write it down. So what gives this bell shape its distinctive shape is, okay, so we'll use so in function notation, then this would be captured by this. So it's 1 over square root 2 pi sigma e to the minus. So this part in the front really is just a constant that ensures that this viewed as a probability density integrates to 1. Okay, and so to remind you, that's the usual way of handling densities in probability, because then if you want to ask, well, what's the probability the random number or the variable falls within 2 bounds, you simply have to do an integral of the density over those bounds, and that gives that gives a probability. And if you integrate over the whole thing, then that gives you 1, which is the almost sure probability of occurrence. Okay, so let's finish this functional form. So you have y minus mu squared over 2 sigma squared, and so here there's two what we call parameters. So this functional form, so it's like e to the minus something squared, right? So it's symmetric around 0, and that gives this distinctive bell-shaped curve. And so you can rescale it or translate it, and so that's what the two parameters mu and sigma squared do. Okay, so in particular, the average, there's names for these parameters because they match their role in this distribution. So mu is the mean, and sigma squared is the variance. Okay, so if you simply just view this as a function of y over the real numbers, then you can see that this bell shape is going to be symmetric around the value mu, and how wide or how spread out it is going to be determined by this scaling parameter sigma squared. Okay, so I just want to relate these statistical parameters, as we call them here, to what we know about functions in mathematics. Okay, so here in this example, I've kind of set the mean to be 0, so this is mu equals 0, and if you want to talk about like the standard normal distribution and z-scores and all those things, then we also use a unit variance. So mu 0 and sigma squared 1 is the standard normal distribution. Okay, so this most famous distribution in statistics and probability. Okay, so I want to use this one to illustrate how to do some Bayesian computations. Okay, so to give a contrived but nonetheless a motivating example, so suppose we have like a new measurement device, like a weigh scale or something, and we want to assess what the error, or how much error that device has, and so suppose it's appropriate to use a normal distribution and to do that, and we're going to take a bunch of measurements. Okay, so we're going to take measurements. So I'm going to measure. Okay, so we haven't done it yet. So I'm going to call these are going to be random variables. So let's say we're going to do it n times. So we're going to record data y1, y2 up to yn. Okay, and I'm going to use the notation we introduced last time. So let's say we want to know on average how wrong is this device. So let's call that parameter theta. Okay, so and just for the sake of simplicity, let's assume we know the variance. Let's just assume the variance is 1, just to make calculations a little easier. And we're gonna say we want to estimate the parameter theta. What's the average bias of this measurement device based on some measurements? Okay, so just notationally, when I write a cap n, so I think this is the same notation in the book. So normal cap n is for normal distribution, and then we have the two parameters. So the theta here is the mean, and the 1 here is the variance. Okay, so for now we'll just focus on estimating one thing at a time. So let's assume we want to estimate the average error, and then that's the parameter encoded here as theta. Okay, so in the Bayesian paradigm, well, we need to set up a prior distribution. So in other words, what do we believe about the value of theta encoded as a probability distribution? Okay, so I will just set one. Okay, and then we're going to come back to this point and talk about prior distributions after the calculation. Okay, so let's to proceed with the Bayesian calculation, we're going to set up a prior. So let's do that here. So I mean, technically, if you want to be really precise, we're talking these are the measurements conditional on theta. Actually, I'll just put it in just for completeness. So this is conditional on, if you know, given the value of theta, then we're assuming the device has bias, theta, and variance 1. Okay, so let's put a prior distribution. So I'm just going to suggest one for the sake of calculation. I'm going to put another normal distribution with a mean 0 and variance 1. Okay, so what does this distribution actually mean? So let's interpret it given this context. So we can use, for example, this prior. So this is the prior for theta, and So from the prior distribution, we can do calculations, and these calculations reflect what we believe about theta before actually doing some measurements. So for example, what's the okay? So in other words, what's the probability that theta is, say, between let's say minus 1 and 1, right? So that could be a question we ask before, which shows what we are assuming about this prior. So because this our knowledge about theta is encoded in this prior, we can answer this question using the prior distribution directly. So this would simply be the calculation probability. So what do we have to calculate? The probability that theta lies between minus 1 and 1. Okay, so how do we do that? This is a standard probability calculation using the probability density. So the density, if it's normal, I just use the function for the normal, integrate that from 0 to 1. So I just have to integrate. Okay, so this is taking the prior, so p of theta before any data, and then integrating that respect to theta from minus 1 to 1. Okay, and so specifically, what is this density? Well, it's just this one. I just need to plug in the correct values. So I'm integrating. So the variance is 1, so it's root 2 pi, and e to the minus. So I'm using the argument theta. So y here is now theta, mu is 0, so theta squared over 2. Okay, so I simply, to answer that question, using the prior distribution, is simply to via this integral. Okay, so so as some of you will know, the normal distribution integral cannot be done in closed form, and so that's why there's all sorts of tables that are used in at least for many of us when we first learned statistics. We looked up these probabilities. So a table, of course, we can also use a calculator or R or any other software to compute these kind of numbers. Now, specifically for the normal distribution, there's a few famous numbers that we may have heard of. So if something is normally distributed, approximately 68% of data falls within plus minus 1 standard deviation of the mean, and approximately 95% falls within plus minus about 1.96 standard deviations of the mean. Okay, so 1.96 might be one of the most famous numbers in statistics, because that is frequently used to calculate, let's say 95% intervals. Okay, so this just to give you some idea, so this is like within 1 standard deviation, so it's about 68% probability. Okay, so how do we interpret this number? Well, according to what we say here in this situation, we're saying before measuring it, before taking any measurements, we believe the average error of this device would be between no larger than 1 in either direction, with 68% probability. All right, Andy has a question. Yes.
Oh, sorry, it's just the camera. Could you shift it's a little bit cut off on the other side. Yeah,
that's better. Okay.
That's all I had. Yeah.
Okay.
Mm-hmm. Thanks.
All right. So that's prior probability calculation. Now, so next, of course, is to integrate where we're now going to measure from the data. Okay. So before we do that, we need to let's quickly recap another point we touched on. Okay, so here we're conceptualizing that we're going to measure. We're going to take this device and we're going to take a bunch of measurements. Now, the typical assumption is that these measurements are independent. Okay, and so last time we had a little discussion on well, how do we know things are independent? And so, for example, in practice, you might need to like recalibrate it, say, before taking a measurement, so that there's no like time correlation in the measurements. So there's of course a practical dimension to it. So let's use our famous acronym. It's IID. So let's assume all these y's up to yn are independent. So that's first I, and then have the same distribution, identically distributed, given the parameter theta. Okay, so let's carry out this mathematically now. How the prior and the data combine to give us the posterior. Okay, so the first rule to remember from last time is that the form of the posterior is to take the prior and multiply it by the likelihood function. And recall that the likelihood function captures how likely are we to see the data that we observed. And so recall that follows from Bayes' rule, which we talked about last time. Okay, so and also remember that the whole Bayesian paradigm is this idea of updating. Okay, it's updating what we know about the parameter as we observe more data. Okay, so we're starting with the prior. So we're gonna after all the calculation, we'll get p of theta given all the data. Okay, and so this is the posterior, and that's proportional to, according to Bayes' rule, two applications of Bayes' rule. So we take, so in practice, we just need to remember to get the posterior, we take the prior, so that's p of theta, not conditional on data, and then multiply by the joint distribution of the data conditional on the parameter, and that's called the likelihood. Okay, so all the ingredients are still here, so we can start off by plugging in the prior. So the prior is this density as we've used down here. So let's just copy that over 1/2 pi minus a squared over 2. Okay, so that's the prior density. Just plug it in. Okay, so now we need to calculate the likelihood function or the joint density of all the observations given the parameter. Okay, so the key assumption here is that we're assuming they all have the same normal distribution and they're all independent. Okay, so therefore this factorizes into the product of independent densities. Okay, so in other words, all I need is p yi given theta, and then multiply one of these for every observation when we can assume that they're independent. Okay, and then to carry off, to plug in this guy, we just need to look up again. Okay, the density of the normal. Okay, plug in the density. So this is a normal distribution in terms of yi, and then the mean is theta, and then the variance is 1. Okay, so we'll plug that in next. Okay, so this part I'm not going to just copy down. And then this part is the density, so 1/√2 pi e to the minus. Okay, so now the argument is yi, because we're talking about the density for yi minus the mean. Mean parameter is now theta squared over 2. Okay, then this just comes straight down times all of of this. Okay, so that's for one of them, and then let me give myself room for the product. Okay, so that's the basic form of the posterior. Okay, so this is the posterior distribution of theta. So this, if you plot this as a function of theta, then you will see after plugging in the data what should be the basis of inference, or for theta. Now that we've seen the data. So the rest of this task simply is to make some simplifications, so that we can recognize what this actually is. And then I'm going to draw some pictures to convince you that indeed posterior distribution you can think of as a compromise between what we believed beforehand, the prior, and then what the data is telling us. So it is indeed a combination of these two sources of information: prior knowledge plus what we learned from the data. Okay, so I will illustrate that. But first, we need to finish this calculation. And also, I'll remind you here that the posterior, this is just a form of the posterior. That's why there's a proportional sign here. Okay, so this this generally is not going to integrate to 1. Okay, if we want to make this into a proper probability distribution, then we can find the appropriate normalizing constant so that it integrates to 1. But first, let's...
Sorry, I have a quick question.
Yes.
It's probably easy for you to clarify. So when I think of a probability distribution,
yes,
like the one you drew, the normal distribution, the probability of a particular outcome,
yes,
is 0, right? Probability of getting exactly a half on a distribution is 0.
Yes, correct.
So it's confusing when we say like probability of yi given theta, that we're actually just evaluating the normal distribution at a particular point.
Yes, correct.
It's not actually 0. So that's sort of confusing to me how we need to get a non-zero probability, we need to have an interval of outcomes, whereas we're evaluating a yi and getting just like the y value on the curve of the Gaussian. So
yes.
Can you clarify what's probability, what's not? Like maybe I'm just mixing.
Yeah. So this is So that's an important point when we're talking about what we call continuous distributions. So where the random value is distributed over, let's say, an interval or the real line, and so in the book's notation we use little p when we talk about density functions. Okay, and so that's why we distinguish density functions from probabilities. So mathematically, I mean, I'm kind of loosely speaking, right? The density is the infinitesimal, probability around that value, right? You can essentially think of that as a limit where in practice to actually calculate probabilities, when you say, for example, what's the so in plain English, sometimes we say, oh, what's the probability that a random person, is, I don't know, 170 centimeters, right? We say that loosely. So specifically what we actually mean mathematically is we probably mean, okay, someone whose height is from 169.5 to 170.5. And so in practice, we would be able to translate that to a probability by actually integrating over that interval. And also from a computational point of view, of course, everything is only measured to a certain degree of accuracy anyway. So technically, pretty much all the measurements we make are essentially discrete, even though conceptually we may use continuous distributions because the kind of true underlying quantity is it can be imagined to be a continuous variable. Okay.
So that makes sense to me. Like, we're basically taking a discrete approximation of the continuous curve in that example you gave with the 170 centimeter person.
Yeah.
But we use the term probability regardless. Like even if if we're using yi given theta, we still say probability, but as opposed to if we were evaluating a point on the curve, the probability is 0.
Yeah.
But we use the term probability interchangeably.
So usually if I say let's evaluate, let's say, the joint density, I would use the word density when it's clear that we are looking at the value of that function, for example, at that particular point, and then probability when we're talking about intervals. Yeah.
Okay, sounds good. Thank you.
Yeah. If the variable is discrete, for example, if you're rolling a die, rolling some dice, then they're interchangeable because there you can assign a probability to every specific outcome. Yeah, it's good. Good discussion. Okay, so we're going to carry out this calculation, and so yeah, the last thing I said was that these things are only up to a constant proportionality. So essentially, we're viewing this as, when we're done all the calculation, we can think of this as a probability density in terms of theta, and we can draw a new curve or an updated density function in terms of theta. Because after we observe the data, remember, we're going to actually measure numbers for each of the y's, and then we can plug in those values of y's into this expression, and then what's left is simply a function of theta. Okay. Of course, in the derivation, we want to keep it general enough, so we're going to keep all the yi's in the expression, and then when we actually show a final curve, we're going to plug in some numbers so we can see visually what's happening. Okay, so everything's up to proportionality constant. So anything, so this is a really useful rule of thumb, is whenever you see stuff in your posterior that is not a function of the argument here, theta, you can just drop it because we don't have the correct proportionality constant at this point yet, anyway, for a probability distribution. So all these, so in other words, all these root 2 pi's are just additional constants of multiplicative constants. Okay, and so therefore, for simplicity, we can drop all of those. Okay, so all we need to focus on is the functional form in terms of theta. Okay, so after I do that simplification, so I'm going to drop these other constants here. So we have e to the minus theta squared over 2. Okay, I'm going to throw out this root 2 pi. Okay, and then I have this product. So I'm going to rewrite that as e to the, so the product of exponentials, so I'll simply sum the exponents here. Okay, so this is what gives the distribution its form. Okay. Now, if you look at this, it's not immediately obvious what distribution this is. Although, if you did skim over the book, you would know that the final result, this is in fact the form. If you plot it, this is actually just another normal distribution, but it's not obvious if you just look at, okay, you're multiplying this exponential of this. Why do we end up with the normal distribution? So that's why I want to go through this calculation. Okay, so this is the form. Now let's work on it a little bit so we can see that in fact this is just another normal density function. Okay, so what I will do first is expand this side. Okay, so let's do here e. Okay, I'm going to write exp. Okay, so then I don't have to write everything in the exponent, just to give a little more room. Okay, so over here I'm going to pull. Okay, so let's pull a minus a half. Okay, so I'm going to expand this thing, and then I'm going to carry through the sum. There's going to be 3 terms here. So the first one is yi square. Okay, and the second one is the cross term, so 2 yi theta summation. Okay, so let's just write it out in full this time. Okay, 2 yi theta, and then the last term is theta squared. Okay, so we'll keep working on that a little bit to simplify.
Sorry, Samuel, you might have to move the camera again.
Oh, I'm sorry.
Yeah, thanks.
Yeah, I probably bumped into it when I'm moving. Thanks. Okay, so this is the form. So let's combine some terms and work with these summations. Okay, so notice the summation have indices I. They only depend. So only the yi's depend on the index of summation. The thetas I can just sum them because there's no I in it. Okay, so we have Okay, so let's continue up here. So e to the minus theta over square root over 2. And then here I have, okay, so after my first set of simplifications, so I have minus a half y squared 2 theta yi, so, and then plus this n theta squares. Okay, so now once I have that, then I can look at this again. So it's now I have everything expanded, and now you look at this term here. Okay, so what is this term? So basically, remember basically you have like 3 exponentials here, right? E to this, and then times e to that, and then e times e to n theta squared. So from the point of view of, remember we're looking at this as a function of theta, okay? So after we have the data, we just plug in some numbers. So this is just going to be a number. There's no theta in this term. So this is yet another multiplicative constant, okay? So you can see how we can repeatedly apply this this rule to simplify this expression. So this is yet another constant. So this is another constant with respect to the parameter theta, so that can be dropped. So basically, okay, so I'm going to write another proportion sign because I'm going to throw away that piece now too. So the remaining pieces have theta in them. So in fact, you see there's a theta squared now in both of these, so I'm going to combine. I can combine those. Okay, so this is minus a half. Okay, so what's left in here is there's theta squared, n plus 1 of them. And then I have minus 2 theta. So, I mean, it's clear that the summation is 1 to n, so I won't rewrite that. Okay, so that's what we have. Okay, so now you're seeing, okay, it's starting to look a little closer to being the final result of a normal distribution. I'm starting to see e to the something theta squared, right? So, okay, so I don't have the form of the normal, but we want to get it into a form such that it's like theta minus something squared, okay? And so this is where we have to go back to one of our favorite techniques from, I guess, high school algebra and do what's called completing the square, okay? So that's the technique that we need to be able to get this into the correct form. So essentially, actually, I should be able to do this just. Okay, I'll write one more line. Okay, so yeah, so I'll do exponential minus. Okay, so I'm going to pull out the n plus 1 and put it in the denominator here. Okay, and so what's left in here is theta squared, 2 theta summation yi. Okay, I divided by n plus 1 here, so I'm going to put n plus 1 here. Okay, and so now complete the square. So this is like a squared minus 2ab, and so we need to put b squared and then subtract the b squared. But it turns out, okay, so let's do that first. So the square completion here is we need. So this is 2ab. So b is this piece. So we need to put summation yi over n plus 1 squared here. Okay, and so if I can't make this appear and so I've got to balance it out, so I have to add and subtract the same thing. Okay, so let's subtract, get it back off. Okay, so that's all right. I need some brackets there at the end, but you can fill it in. I don't have room. Okay, so here, so I've kept, so this is the same quantity as the one above. Except I now have a perfect square in here, And now, the key point here is I can actually do this, and it's allowed because this thing here, so this term actually is not relevant because it is yet another constant because there's no theta in it. Okay, so this is yet another multiplicative constant because it's inside the exponent. Okay, so in fact that can be dropped in the constant of proportionality. So this is just proportional to. Okay, so now I have completed the square. All I have here is theta minus this piece. Okay, and then this one is just another constant. So that's what's thrown away when I do this proportional to here. Okay, so that's the final result, and now we can actually recognize that this is indeed a normal distribution. Okay, because this is e to the minus, and then there's this bunch of stuff, and so if you look at the expression for the normal density function that I wrote at the beginning, you can now recognize what is mu and what is sigma squared in this expression. Okay, so if you look back at that, it's basically just matching it up, okay, which is the normal density. Okay, so what is mu? Well, mu is the thing that comes in here, so the mean is summation y over n plus 1. And then, what's in the denominator here? Well, so in the normal density, it would be theta minus mu squared, and then in here, and then over 2 sigma squared. Okay, so therefore, we now know that the variance of this, we've now identified what would be the variance of this normal distribution. It's 1 over n plus 1. All right, any questions on that?
Maybe not a question. I just because it's kind of a mixed audience. Just want to kind of show of hands. Are people okay with the calculations? I know not everyone's. Maybe it's been a while since they did integration or seen a product sign and sums and all that. Like just Jennifer and Christiane, are you okay following a little bit or?
Yeah, don't be afraid to ask because some of you, this may be very new to some of you, so just jump in. Yep.
It's complex, but I'm doing my best to follow along.
Okay. Yeah. Okay. Yeah. No, I understand. Let us know if questions halfway through, because I realized as Sam's been speaking that there's some prior assumptions about the math background.
Yeah, for sure.
So don't be afraid if you have questions. Just shoot a question.
Yeah, for sure. Yeah, because I noticed, especially with this example in the book, they even skipped most of this, right? They just said this is an exercise. So, so I want to make sure you can actually see basically we're repeating. So remember the key principle, the takeaway is how do you get your posterior? You multiply the prior and the likelihood function, okay? And then everything else that doesn't depend on the parameter is just multiplicative constant. So that's been a fact that I've used at least 3 times, right, in this derivation. And often, you don't need to do this sort of thing. Here I just want to carry out these details to show you indeed that the resulting posterior in this problem with this setup is another normal distribution. Okay, so that's the key takeaway.
So if we had a different prior distribution, do you preserve the distribution to the posterior given the prior distribution, or does it change depending on the distribution?
Absolutely. So that's an excellent point. It changes depending on what prior you use. So if I want in this problem, okay, so I'm estimating the mean of a normal distribution, right? That's the context. If I want the posterior to also have a normal distribution, then I have to put what the book calls and is commonly called a conjugate distribution. So you may have seen that term in this chapter. So a conjugate prior distribution preserves the family of distributions so that the family from which the prior is and the posterior is the same family of distributions. In practice, that's more so. I would say it's more so a technique for computational convenience, more so than having any fundamental reason for doing that.
So if you did this example and you totally misjudged the prior, so you thought it was a normal, but then all your sample y's are just like a 0 and 1 or something, like they were terrible.
Yeah.
This is obviously going to become more and more like spread out, but it stays a normal, which I'm surprised. So like if your prior is just a terrible choice, you're going to get garbage output no matter how many samples you take. It's just going to like almost flatten out or something, or
yeah. So that's a subtle point, but I think it's since we're here, it's good to bring out the distinction. So in that case, okay, so suppose all your y's end up being like 1 or -1, right? And then it's not normal at all, right? So that's actually not a fault of the prior per se, but it would be a fault of the model you're assuming for the measurements. Okay, so there were two distinct assumptions. We made an assumption about the prior, and then we also made an assumption about the likelihood part. We assumed that the measurements are going to be normally distributed. Then in that case, it's not the prior that's at fault, but we want to go back and look at, okay, why did we assume the measurements are going to be normal when they're not actually normal?
Okay.
So yes, that would be an important modeling step, and that would lead us to question whether we're putting the right model in the measurements. Yeah.
Okay.
Yeah. Okay. But the prior could still see. I mean, there's in the chapter there's a really long discussion about priors and how you choose them. And so since we're already kind of talking about it, I'll just make a few more comments. So for computational convenience, often we have the conjugate prior, so that the family of distributions that the prior comes from and what the posterior looks like at the end is the same family of distribution. In this case, we put a normal prior on the mean, and then our posterior for the mean is also normal. Okay, so that's known as the conjugate prior. And the other kind of case is what's known as the non-informative or vague or diffuse priors. The prior, we can also put priors that suggest that we don't know very much about the thing, whatever quantity we're estimating. And so, so from a probabilistic point of view, the usual way to encode that is some sort of a uniform distribution. So basically, you just say you're estimating the probability of success and you have no idea what it is. So you just say I'm willing to assume any number from 0 to 1 is equally quote unquote likely. Okay, again, we were talking about density, so it's not strictly a probability, but we're saying like any, if any, we're willing to assume like any interval within that range is equally likely, then basically you just draw a flat line, which is a uniform distribution. So there's many ways to construct priors, and the other half of the goal of today was to have a little discussion after I finished this example on how we could envision, let's say, priors in some practical applications, like our health application that we'll be tackling. Okay, so just keep that in mind. And I will finish this. I'll wrap up this part by simply finishing this derivation by plugging in a couple numbers, so you can see and then draw a picture for you. Okay, so I'll keep this final result down here, and then I'm going to plug in some numbers, and then you'll see visually how the posterior is in fact a compromise between the prior and the data. Okay, so let me give some numbers. Let's say we measure this. We take some measurements. Let's say we do. Let's do like 9 measurements. Okay, so then n plus 1 is 10. Okay, so it's easy number to work with. Okay. Okay, so suppose we now observe our data. Okay, assume everything works nicely and we get independent measurements. Okay, let's say we take 9 measurements, and then the average, let's say, is 3. Okay, so the summation yi over 9, so that's the average, would be, let's say that's 3. Okay, so according to, so remember the prior was, theta was normal, mean 0, variance 1. Now the posterior, so theta given y, the y's, 9 of them, is, from our derivation, is also normal. Okay, so now let's see numerically what this is. Okay, so summation, so the average is 3, so summation yi is 27. 27 divided by 10, so that's 2.7. Okay, and then the variance of this is so 0.1. Okay. Okay, so now you see, indeed, this is just a function of theta once you plug in numbers for the measurements. Notice I didn't even have to give. So this is a subtle point, but worth mentioning. In order to get this posterior, I didn't need to give you exact or specific values for each of the y's. I just told you essentially I gave you the average of the y's. And in fact, because in this case we're willing to assume that the measurements are indeed coming from a normal distribution. See, we haven't tested that, right? But assuming that's a valid assumption, then to get the posterior, all I need is to know this statistic, which is the summation of the yi. So that's called a sufficient statistic. So in fact, once you know the total or the mean of the yi, you don't need to know anything else for the purpose of estimation in this model. Okay, so the last thing I want to do is simply draw some pictures to illustrate what has happened between the prior and the posterior once I have these numbers. Okay, so here's a picture. Okay, so before we observe any data, the prior has mean 0 and variance 1, so it's simply the standard bell curve around. Should be a little slightly more symmetric, but you get the idea. Okay, so that's your prior. Okay, and I'll use some different colors here. Okay, so that's the prior distribution. Now let's also draw the posterior. So the posterior is centered at around 2.7. So let's put that here. So peak is here, and it's really narrow now because the variance is 0.1. So standard deviation of this is square root of 0.1. That's around like slightly over 0.3, right? So it's going to be a lot narrower. So let me try to mimic that. So it's okay. So it's going to be, it should be slightly more narrow than that, but that gives you the idea. So you see after observing the data, your prior has now shifted, right? It's shifted a lot closer to what we say is what the data says. Okay, so why is 2.7 much closer to what the data is telling us? Well, remember theta is the mean of distribution, right? And so in the data we observed, what was the actual mean in the data? Well, it was 3. Okay, your prior mean was 0. Okay, so your posterior mean, according to the Bayesian paradigm, intuitively would be somewhere between 0 and 3. Okay, and so specifically in this example with 9 observations, after combining the data with the prior, we end up with a mean that's fairly close to the data, right? 2.7. So we want to add another line. If you were to trust it simply the data, then you would have 3. Okay, so this is the sample mean of the data mean. So 3 is the sample mean of the data, 0 is the prior mean, and then 2.7 is your posterior mean. Okay, so that gives you a visual to see how, after carrying out the calculation, in fact, the posterior distribution. So there's kind of a couple takeaways. Posterior is going to be somewhere between what you would expect from the prior and what you would expect from the data. So it's a compromise in that respect. And the more data you have, then if you have more and more data points, this is actually going to shrink to a more and more narrow distribution. Okay, so that gives you a visual to see how Bayesian inference, or the basics of how Bayesian inference works in the most famous distribution, which is the normal. Okay, so those would be the key takeaways I want to give you from that. Okay, any questions on this before we move to a discussion? Yes.
So it's pre-encoded into this method the balance between the prior versus like the distributions, which one we believe to rely on more. Like it's we don't get to choose our reliance on which is more important. Like it's built into it already.
Yes.
So
yes.
like
that's right.
we can't assume the prior is more valid than the data, because that's sort of an assumption of this whole framework, right? Like,
yeah. So so the framework it's principled in that sense. Once you set the prior and you assume a model for your data, then the rest of it is just algebra, right? It follows. So if you so generally the more data you have, then the closer your posterior is to the, in this case it would be, if you have more data points and the average is 3, then this will get pushed closer and closer to 3, right? So eventually data will overwhelm whatever prior you choose. Okay, so the role of the prior, I mean, sometimes it's in practice, if you, in many applications, the weight of the prior actually becomes quite negligible once you have enough data. Pretty much, even if you put a much stronger prior, so if you made this prior variance much smaller, for example, that would be one way to encode, like, you're more certain going a priori going into the analysis. In which case, it will take more data to override your prior beliefs. So that's how this whole paradigm works.
Okay. Thank you.
Yeah, that's a good discussion point.
Just maybe a kind of related question. So if you take more and more data, I mean, it's conceivable that the next 10 to 100 data is somewhere else, and then you'll ship the thing that way. But does it say that if you take, as n approaches infinity, that it'll kind of converge to something, like it's going to settle? Like, I guess that's the central limit theorem.
Yeah, exactly. So, it's not here anymore. But you saw how the mean of it, right, was actually I'll rewrite it because this is an interesting point. So remember the mean of this green guy, right? It was summation yi over n plus 1, right? So essentially, when in the limit, right, when n is quite large, okay, so you know that summation y over n is simply the mean, right? That's the sample mean, or y, or what statistician usually would write as y bar with a bar on top, right? So essentially, the prior is really just adding a 1 here to the denominator. Okay, so if you're putting a stronger prior, then this would be this would just be it could be like a larger number, right? But eventually, you see in the limit, any prior is going to get overwhelmed by the data if you have a very large sample size. And similar for the variance, right? The variance is 1 over n plus 1, right? So essentially, once you have, that's going to get overwhelmed such that it's going to shrink to it's simply going to shrink to the sample average when you have a ton of data.
Okay, thank you.
Yep. Okay, any questions from the students? Or go ahead, yes.
One more, sorry. Thanks again. So when you did say that if we were more confident in the prior, we would use a steeper prior.
Yes.
So that would be a smaller variance, right?
Yes.
The variance is in the denominator of the exponent. So that would then show up in the denominator of the that would show up in the mean of the posterior, right?
Yes, it shows.
So
it shows up in here.
To 0, as you suggested.
Yeah. So if you want a stronger prior, you might put like a 0.1 here, right? So then this would be what is it? It's related to that number. I don't remember the exact algebra. I mean
you should pull it closer to 0 as you suggested. So that's cool.
Exactly. Yeah. I think it would be 1 over. I think this would actually be 1 over 0.1. Yeah. I think that's the relationship. Yeah.
Jennifer, you had a question there you wanted to ask?
Yeah. Yeah. Along with that, I understand that to get the two, I guess I'm just struggling a bit to understand how you got the 2.7 exactly. Like, I understand that, because the denominator is n+1, it's going to be slightly smaller than 3, but I'm just kind of stuck on how you got that exact number.
Yeah, so this, yeah. Okay, so we're assuming in this case that there are 9, we measure 9 times, and so summation yi would be 27, right? If the average is 3. So this is just
okay.
this is just 27 divided by 10. Yeah.
Okay, that makes sense. Thanks.
Is that helpful? Yeah. Okay.
Any other question, Sun or Eleanor or Christiana?
No.
Okay. All right. So yes, Sun, you have your mic is.
I don't have any questions.
Okay. All right. Okay. So in that case, I will conclude this part, and then for the rest of the time, we can have a little bit of more of a practical discussion about priors, especially as some of us are interested in tackling some applied problems, and so priors, of course, play as we explained a key role in setting up the Bayesian analysis. Okay, so let me just turn that off, and then I will rejoin you.